But just briefly, this is just a screenshot of the announcement on Canvas. So we have released the exam 2 grades. Oh, pretty good, better than last time. This is broken down by section. So as a reminder, the sections are graded separately. There's 6220 and there's 4220. And the mean and the median in both are similar, so within 1%, 76-ish, 75-ish, and then in 4220 it's like 70.14 and 70.35, so those are very similar. And yeah, max is 100, standard deviation in 6220 is about 15.5, in 4220 there's just less students, I think it's maybe about 100 or so in 6220, and about 50 or so in 4220, so with fewer samples, the standard deviation goes up. Questions, issues? So if you have any questions or regrade requests, you can raise them directly on Gradescope. Yeah, we are not releasing the solution set, but if you have any questions about any of the topics or the exact questions, you can feel free to ask in the office hours. Any issues? So we have one more exam. We have a final exam sometime. Yes, please go ahead.
I'm just wondering, based off these exam scores, do you foresee the class being curved for either section?
Yes, probably, but I can't tell what it would be until we have the final numbers. Last year, I think maybe about 85 or 86 was an A, but it obviously depends. But that was about 50 students, and this time it's about 150, so it's hard to make the comparison. Any questions? And they would be curved differently because, like I said, the different sections are graded differently. Any questions? Okay, yeah. So we have one more exam. We have a final sometime in the exam period, whenever they have assigned us according to the matrix. I think unfortunately it did at like 8 a.m., so we're gonna have to make it one day. Okay. Moving on. So going back to interconnects, as a reminder, last time we had ended up with hypercube networks, and before this, there's like a big table about different measures like section width and cost, distance, and so on. And we were talking about arbitrary dimensional mesh. And the reason that we're interested in maximizing the mesh dimension is because one of the good things grows faster than one of the bad things grows when you maximize as a function of the dimension. And yeah, these are some examples. If you had number of processors equal to 32, given if you could choose the dimensionality, what are possible dimension lengths you could set? And the maximum dimension for p equals 32 is 5d, because that would be 2 by 2, and 2 by 2 by 2, so 2 raised to the 5. And you can't go any further, because if you made this 60, one of these dimensions would have to become length 1, which would just be reduced to one dimension less. So like, for example, a matrix that's like n by 1 is just a vector. So that's the reduction from n plus 1 dimension to n dimensional. And yeah, so to maximize the dimensionality, you can choose the variable amount of dimensions based on p. If p is a power of 2, so for p raised to 2 to the d, we should choose d as the number of dimensions. So it turns out that there's this nice connection between hypercubes and meshes. So previously we were embedding 2D meshes into the hypercube and back and forth. And it turns out that if you one way to think of a hypercube is just if you made the dimension as large as possible. So if you have 2 to the d processors, yeah, the maximum dimension is d. And so from there, you can just get the parameters of the the measures of the hypercube, such as diameter and bisection width, by just plugging in the dimension as the parameter in these closed form functions. And so the diameter, which is the longest path through the graph between any 2 points, is log p, because, yeah, so d is log p, because p is just 2 raised to the d. And the diameter is the maximum length between any 2 points in terms of number of hops. And we know that if the bit string that you represent the nodes as has length log p, then the maximum distance, the maximum number of bits you have to flip is log p. to get between any two bit strings, and yes, the maximum you have to flip is log p, and that's the worst case. And you can flip 1 by moving between any neighbor. The bisection width is p over 2. So remember that the bisection width is how many edges you need to cut to disconnect the entire thing in half. And that is p over 2 by just putting it in as a function of d. And yeah, this part, how do we address the processors in the hypercube? We have been doing this for a while. You represent every node in the hypercube with a bit string. And if you want the neighbor along some dimension, you just flip it 0 or 1. So now one way to view the bit string that we have been addressing in the nodes in the hypercube is a tuple of which processor you are along that given dimension, 0 or 1. And to find the neighbor, then you flip the bit along that same dimension to go to the other one. So this is what I was saying, if there's d dimensions, we have been doing this bit string, and then now we can view this bit string as a tuple of coordinates in however many dimensions you have. So this example is which processor you are along each given dimension, 0 or 1, and here we have 6 dimensions. The neighbor along the dimension, if your coordinate in that given dimension is 0, then their neighbor is the same, with all the other ones fixed, but switching it to 1, and vice versa. If you're 1, then the neighbor is 0, if you flip it along that dimension. And in some sense, if we view hypercubes as this maximum dimensional mesh, then every processor is a corner processor, also dimensioned. So previously when we had 2D or 3D, in 2D there are 4 corners, like left, up, right, and so on. But now in the hypercube, sometimes every corner, every processor is the corner, because there's only 2. And yeah, since it's just 0, 1, we just represent this tuple of coordinates as the bit string in the hypercube. Questions? So in some sense, this is telling us that previously we were doing embeddings between mesh and hypercube, and one way to see what this is just that embeddings are moving lower dimensional meshes into the highest possible dimensional mesh, which is a hypercube. The distance is at most log p. Every node has log p neighbors, because you can have log p positions where the bit can flip. So that's where you get the neighbors from. And the distance between any two nodes is however many bit positions they differ in. So it's bounded above by log p, but it can be less. One cool thing that this gives you is that if you, so far we've had this bit string representation of the nodes in a hypercube. And if you view hypercubes from increasing in the number of bits, you can kind of think of it as this recursive definition where you can build higher dimension, like larger hypercubes from smaller hypercubes. So the smallest one is just 0 bits, there's 1. If you have 1 bit, you can have 0 and 1, so there's just this one connection. And there's distance between 1 and 2D. So now you have 2 bits, so there are 4 possibilities. And you can think of this as being constructed from the 1D hypercube. So 1D, this is just a line, and it's kind of copying this thing repeatedly and then making connections between the 2 copies. And then similarly from 2D to 3D, you can think of this as copying the plane twice, and then just drawing connections between the nodes in the plane. And then going up higher is getting more complicated, but then you can copy, again, this 3D twice, and then connect between the nodes of the 2 copies. And one nice thing about this is that if you actually had a true hypercube, then this would make it really easy to subdivide. So one common case is like you have a large cluster and you have many people using it and you want to distribute resources across those people. And one way to do that is if you have a true hypercube, you can divide it recursively. So you can easily there's easy definitions of half of the topology, and you can split them between the users, and half by half, I mean like half down recursively. So we have been doing hypercubes for a while in this class because they map nicely to a lot of the algorithms that we've studied. One problem when actually trying to construct hypercubes is when you try to build arbitrary dimensional hypercubes, the number of neighbors is variable. So if you go up one more dimension, the number of neighbors that every node has to have goes up by one. And the problem with that is, in reality, like when you have a machine, it has a fixed number of input and output ports. And that thing it doesn't grow with log. It just is fixed when you buy it. So it is difficult to build these arbitrary dimensional hypercubes. And for a while, people were trying to build true hypercubes, but I think that has mostly stopped now because of this challenge. And yeah, another issue is that when you try to build higher than 3D, the links will often cross. It's hard to embed them into 2D space. And also, the cables are non-uniform length. So it was easy when you have like a square or a cube, but it becomes harder when you try to go up to 4D, 5D, so on. So rather than actually building the full hypercube, what people actually do is basically try to flatten the thing and spread the links over stages in time. So this is similar to, if you remember, when we were doing embeddings, and we had this tree embedding. And in the tree embedding, it wasn't that you used the whole tree at one time, it was that you used different levels of it at different times in the algorithm. And so that is similar to this technique, which is going to be trying to flatten the thing and spread the links over stages in time. And that fits well onto a lot of algorithms. Like, for example, in Pythonic sort, you use the full hypercube, but at each phase, you just use one distance, like either the farthest distance, or you use distances in powers of 2. So you're not using all of the distances at once. You're just using one of them in each step. So the thing that flattens the hypercube is called the static butterfly. And this is just another type of interconnect. And so it makes this trade-off. Normally in a hypercube, you would have p processors. We increase the number of processors to p log p because there are log p potential neighbors or potential phases. And so each column of this has p processors, and there are log p columns because each one of them is a different level, different distance of connection. Like this is distance 4, distance 2, distance 1. And the crosslinks are the hypercube links, and you can also have pass-through just to the same processor. So the processor IDs are the same as they would be in the hypercube, but in each phase, you just have to, the distance is fixed in that column. So there are p log p processors. Actually, in reality, these are probably switches. So if you remember, switches are like these other units that you can either, like there's 2 inputs, and you can route to either, you can pass through in the outputs, or you can swap the wires in the outputs. And switches are lower, they have lower functionality than processors, and they're cheaper to build. So when building these interconnects, you can build them out of processors and switches. And so to do this routing in between would probably be switches. And the point of this is to route hypercubic permutations. Yes. Yeah. So these are processors, and then the middle ones, you're just trying to either pass through or move it down along some output wire. Like every node here has 2 inputs and 2 outputs, and you're trying to figure out it gets some input and it has to output along some wire, depending on what the algorithm tells you. Like, for example, in some of the algorithms, you want to pass on something to distance 2 away from you. And so that's what this routing would be. But it doesn't, these internal things don't need to be processors because those are heavier weight, and so they could just be switches which just pass through either on the higher wire or the lower wire. Any questions? So this is what I was just saying. The most basic switch is like this. There are two options. So there are two inputs always, and there are two options for how it can go. You can either just, something comes in here and you pass it through on the top output. Something comes in the bottom and you pass it through on the bottom output. Or you can have this option where they swap. So something comes in the top wire and it comes out on the bottom wire. Or it comes in the bottom wire and comes out in the top wire. And this is called crossover, and this is pass through, based on if you swap which one it comes in and out. And so there's one network, or a network, that can arbitrarily route these hypercubic permutations. Later on, we'll see, it's called the omega network, but it's based on this idea of perfect shuffle. So the way that perfect shuffle works is that you start with the numbers. Let's just say here we have 8 processors, 0, 1, 2, 3, up to 7. And in each round, in each column, you put together 2 new processors. And the point of this is to try to minimize the congestion when you route the hypercube. So you could probably route hypercubic permutations through many architectures, or through many interconnects. But one thing that we want to try to do is route them efficiently. And by efficiently, I mean that there's no conflict when you try to route them in your processors or in the switches. And so the way that this works is you can kind of imagine it if you had a deck of cards labeled 0 through p-1, and you split it into left and right. So in the beginning, the deck of cards is 0 through 7. And you split it in half, just in the middle. So the first half is 0 through 3, and the second half is 4 through 7. And to do the shuffle, you just take one from the left and one from the right, and you make a new pile of length p. So taking one from the left, 0, then you take one from the right, 4, take one from the left, 1, take one from the right, 5. So that's where this 0, 4, 1, 5 comes from. And then you do the same thing, you just keep going, 2, 6, 3, 7. So that's 2, 6, 3, 7. And then you can repeat it. So now you have another stack of length p. And you split that in half. And you do the same procedure, where you take one from the left and one from the right. So 0, 2, 4, 6, 0, 2, 4, 6, 1, 3, 5, 7, 1, 3, 5, 7. And if you repeat it again, then you'll get back the original order. And these define the connections. So the connections through this thing are just from the numbers to each other. So in column, so like here, 0 is just passed through always, but 1 is passed down to 1 again, 1 is down here, and up there when you do the shuffling. So the lines are just connecting the numbers themselves, like 2, 2, 2, 2. Questions on how you do this construction? And then shortly I'll go through some examples of how you actually use this. But first, the first step is just making the connections and making the order in the columns. And the omega network is based on this perfect shuffle. So this omega network has p over 2 times log p switches inside. So there are p over 2 switches in each column because you have p processors, and so each of them, like each switch has 2 inputs and 2 outputs. So that's why it's p over 2. And then log p is because there are log p phases, or log p columns in this network. And basically the way this works is that you group, starting from the top, just group by 2 to define these switches. So the input and the outputs are just given by this thing. But this is like if you had drawn a box, 2 here, 2 here, 2 here, and 2 here, for all of them. And then you can interconnect network with switches in the middle. And so it has some processors on the left and some processors on the right. And the goal of this is that using these switches, we're going to route through permutations. And permutations are just, for every input processor, it maps to some upper processor. And a hypercubic permutation is, for every input processor, a fixed bit flips for all of them. And the bit is shared. So like it could be the most significant one, for example. All of them flip the most significant one. And so this thing, it can route arbitrary permutations, but you can show that it can always efficiently, with no contention, right, route hypercubic permutations. And so when you want to route through this thing, actually the algorithm is extremely simple. It's called destination tag algorithm. And the way it works is that you start from some processor. So just for now, we can focus on the case of just routing one single source and one single destination. And here, suppose that we want to route 010 to 101. And the procedure is like this. If you see 0 in your given column, so the number of columns is equal to log p, which is the number of bits. And it's only based on the destination. It doesn't have anything to do with the source, and except for the starting point. And it works like this. If the bit is 0, then you output it on the top wire. If the bit is 1 in that given position, you output it on the bottom wire. Or sorry, 0 is the top one, 1 is the bottom one. So here, just looking at the output, 101. So we started at 010, which only connects to this box. The top bit is 1, so we output it on the bottom wire. The middle bit is 0, so we output it on the top wire. And then the bottom bit is 1, so we output it on the bottom wire. And now you can see that this output is 101. So it did route it to the correct processor. So why does this work? So one way to view the perfect shuffle is that in every column, you flip one of the bits. The neighboring pairs have one bit flipped, and the bit that's flipped changes. So if we go back here, this pair is 0 and 4, which is 0 and 4 here. And in binary, 0 is 0, 0, 0, 4 is 1, 0, 0. So the top bit is flipped. And same for all the others. The pairs 1 and 5, 2 and 6, 3 and 7. They're the same except for one bit that is flipped. And then this, if you look at the second column, which is this one, 0 and 2 are the same except the middle bit is flipped. So 0, 0, 0 and 0, 1, 0. And then same for all the other ones. The difference between 4 and 6 is that only the middle bit is changed. And then similarly in the last column, these pairs are the same except that the last bit is different. So the top one, 0, 0, 0 and 0, 0, 1. 2 and 3 is 1, 0, 1, 0 and 0, 1, 1. So, and the bottom one is the one that has 1 in the flipped bit, and the top one is the one that has 0 in the flipped bit. And so that's why this destination tag routing works, because the top is 0 and the bottom is 1. Yeah, this is basically what I was saying. So this perfect shuffle brings together the elements with flipped some bit. In this column is the most significant one, but in the later ones, it's just from top to bottom. So the number of stages or columns is log p, and each column, the pairs are all the same in log p minus 1 bits and different in 1 bit, and that 1 bit changes depending on which column you're in. So one question, or I guess maybe you'll see it on homework, but like one question that comes up with this is, first you have to build the omega network, which you can build by doing the perfect shuffle, and then you route permutations through it. And so, like a homework question, for example, could be first draw the omega network on 8 processors, for example, and then given this permutation, draw the paths for each source destination pair through this network. And so that involves first knowing how you do this construction through the shuffle, and then second knowing destination type algorithm to route the permutations based on the destination bits. Are both parts of that clear? So you can effectively route hypercubic permutations, but you may not be able to route arbitrary permutations. So for example, you may not be able to route arbitrary permutations efficiently. So let's look at this example. So we have 2 source destination pairs. One is going 0, 1, 0 to 1, 1, 1. Another is going 1, 1, 1 to 1, 0, 0. So this is not a hypercubic permutation because this differs in 2 bits from here. And these 2 differ in 1 bit, but it's the middle one, which is different, also different from the 2 that it differs in on this end. So here you can see that both of them are trying to go out this connection between A and B. So that's why there would be congestion, because you can only transmit one message along this wire at a time. And they're going out different places in this B box. One is going out this way, one's going out this way. But they're going in 2 different ones to this A box, but they're just trying to go out the same wire between A and B. So sometimes the questions can be of the form, given an omega network and given a permutation, can it be routed efficiently through this thing, or does it encounter some cases where there's congestion? It can, sometimes, depending on the permutation, even if the permutation is not hypercubic, it sometimes can be routed efficiently. But, so it's not like if it's not hypercubic, it can never be routed efficiently, and if it is hypercubic, it can always be. It's like, in some cases, even if it's not hypercubic, depending on how the output bits go, it may be able to be routed efficiently. So you just have to run through the examples when you have questions like that. This is an example of routing a hypercubic permutation. So here, 0, 0 are, so this is just flipping the top bit. So 0, 0, 0 goes to 1, 1, 0. 0, 0, 1 goes to 1, 0, 1, and so on. So these are all the paths through this thing, and some of them cross over here, and the rest of them are passed through. And the reason that there's no congestion is because you can show that, given the construction of this omega network, in the hypercube, one of the phases, or one of the columns, will have crossover, based on, because the construction of the hypercubic permutation is that one bit is flipped. So from the input to the output, one of the columns will have crossover, and the rest of them will be passed through. But none of them will conflict on the wires. And that's why you can do the routing efficiently. Questions?
Are the processors on the left side and right side the same?
Yes.
It kind of has some.
Yes, good point. Yeah, so you can imagine the one on the right kind of like wrapping around to the ones on the left. They are the same. Yeah, because just because you probably don't have 2 sets of processors. So I think that's it for that part. So we're going to do this matrix vector. So we do sparse matrix vector. This part is a bit more practical. It's less theoretical than the previous part on interconnects, but I included it because I think it's interesting. Back in 1990, this guy, Harry Markowitz, won this Nobel Prize in economics, and one of the observations that he had made, even back in the 90s, or he won it in the 90s, but he was making this observation in the 50s, that in many practical matrices, a lot of the entries are zero. So he called these matrices sparse, because out of all possible entries, only very few of them relative to the possible entries are actually present. And if you have started the homework, you will understand this. Or sorry, not the homework, the programming assignment. So the definition of sparsity is, it's a little bit fuzzy, but I think one good heuristic definition is that the number of zeros is greater than 90%, or in many cases often much greater than 90%, like 99 or 99.9% zeros. And so only 1% of the possible entries are actually there. And there has been a lot of work on trying to develop special data structures and algorithms for sparse matrices, because if you have a sparse matrix where most of the entries are zero, you can sort in a dense form, like in an adjacency matrix, but then you're going to be wasting 90% of the space, or 99% of the space. And also, if you try to run algorithms on that thing, almost all of the actual operations you do, like, will be multiplied. For example, if you do matrix multiplication, almost all the actual operations will be multiply and add by zero. So there's no point in actually doing them, because the only things that will contribute to the output are when you multiply and add two actual elements together. So they come up in many, so this is one picture. There's this sparse matrix collection that you can download many sparse matrices from online, and they provide these pictures, like some visualization of where the elements are. They come in a lot of applications. For example, climate simulation, images, page ranking for search, and graphs, especially including graph neural networks, but most graphs are really sparse. Like, for example, if you think of social networks, and the vertices are the users, and the endings are like the connection between the users, that graph, if you represent it, almost all the connections are not there. You usually have small clusters, or like maybe some vertices are well connected, but almost all the vertices are not. And there are many structures, many possible structures of sparse matrices. So some common ones, one is diagonal. So the colors are where the actual entries are, and the empty is just zero. So diagonal is all the entries are along the main diagonal. Tridiagonal, we have three main diagonals that are covered. And the general form of that is generalized diagonal. You can have some arbitrary diagonals. Another one that comes up sometimes in practice is blocked. So sometimes from some applications, the non-zeros exhibit this block structure where they're clustered together. This is symmetric, so that means it's reflected evenly across the main diagonal, and then irregular is that there's not really clear pattern about where they are. So you can see them in many places. Internet connectivity, so these are just the pictures of the non-zero structure. Structural design, linear programming. So they occur in many different applications, and they can look different depending on where they came from. Yeah, another one is a recommendation matrix. Like if you have people on this side and products, and the entries are the ratings. In most cases, people will have not rated anywhere close to the full number of products that are available. So that's another example of sparsity. So we only probably interact with a few of the products for each individual user. More possible applications, graphs. So like I said, like the PageRank for the internet, and transportation networks. So if the nodes are, for example, like the intersections, and the roads are the edges connecting the nodes. Most of the intersections are not connected to most of the other intersections because of paths through the transportation network. For text analysis, if you have the matrix of words, and then a lot of them come up in science and engineering problems, like differential equations, optimization problems, and simulation. Any questions so far? So the point of that was just to motivate, like, why are we interested in studying these specific form of matrix, and I guess more going forward, like, why are we interested in making specialized formats and algorithms for those? The reason is because you can save a huge amount of space and computation time by specializing your representation. So the first step to doing the algorithms is that you have to store the matrix. So in the sparse matrix formats. And we have done these in the past. These are just the same as we had discussed when we were doing, a while ago, we were talking about representing graphs for like MPI topologies. These are just the same formats as back then. So the most basic graph representation we have, or matrix representation, is a GCC matrix, which is just you directly store the matrix in a 2D grid. And you can use it theoretically for sparse graphs. It's not incorrect in the sense that you will store all the values, but for large-scale sparse graphs, it is probably unlikely that this full realization can actually fit in the memory, or even in the memory of many machines. Because the size of this is quadratic, but in reality, usually the size of the number of non-zeros is linear, and the number of non-zeros are just the actual entries. Usually, the number of non-zeros is closer to linear in the number of rows rather than quadratic. So if you can make a special representation, you can reduce the space quadratically. And there's this duality between graphs and matrices. Any representation that you use for sparse matrices can also be used for sparse graphs, because you can store a graph as a GCC matrix. This is just like the weights. So 0 to 2, 0 to 2 is 26. So usually when you read in the matrix, so when you download something from SweetSparse, or the sparse matrix collection, you get a file. Basically, each line is a 3-tuple. Each line has 3 entries in it. One is the row, one is the column, and one is the value. And so if you had k non-zeros, the length of your file is like k plus 1, because the first line is how many rows, columns, and how many total entries there are. So there's a little metadata at the top, and then the rest of it is just one entry, one per line. So when you read in this single file, this is what you get. It's called coordinate representation, and it's just a list of, it's row index, column index, and weight. And so if you have a GCC matrix form, it is really easy to write this out, because you just iterate through this entire thing, and if you see something, you would output it as a tuple. So this is what you get when you read in the file. This is also what you get in the homework, in the distribution. One thing about this is that it's easy to modify. Like if you wanted to add a new tuple into it, you would just append it to the end. And if you wanted to build it, it is really easy because you just list out the tuples that you have. Is it sorted? When you read it for file, usually it's sorted, but it's not necessarily guaranteed to be sorted. Yeah, if you want to maintain the sorted order, it's hard to figure out where it goes. Usually you don't use this as a sorted representation. tabular representation, and you probably also wouldn't use this to run algorithms. Other questions? Another way, so you can, I'm not going to go through this right now, but you can convert between any of these representations. If your representation allows iteration over the non-zeros, which any reasonable representation should allow you to do, you can just convert the memory representation between the two. Another one is adjacency list. So from this matrix, you can store, it's basically a vector of linked lists, where each entry in the vector is a pointer to a linked list, or null if there's no adjacency. And each entry in the linked list is two fields, a destination, and the value, and is a pointer. And the source is stored implicitly in the adjacency list. So all the entries in row 0 are in position 0. So you don't need to actually, these sources are never actually written anywhere. But if you want to get, for example, if you want all the non-zeros in row 3, for example, you would start in row 3 and you just iterate through this linked list. And we did it by rows here, but you can also do it by columns. Like then every entry in this vector would be corresponding to one column, and then the coordinate here would be the row index. And sometimes in some algorithms and some matrices, you prefer to iterate through the rows. Sometimes you prefer to iterate through the columns. So that's why you may store it one way or another. And in reality, probably the most used representation to actually run the algorithms is called compressed sparse row, or CSR. CSR is basically just making the adjacency list more cache efficient by locating them all together in one array. CSR has in the weighted case, it has 3 arrays. One is pointer, there's index, and value. And you can think of that as basically linearizing the adjacency list that we just had in the previous slide. So this is the adjacency list, and we have 0, which is, so pointer array indexes into the start of that row's neighbors, or that row's non-zeros in the adjacency array, and the index stores the column IDs in the CSR, and then the value is just the values. So if you wanted to run, so say for example you wanted to iterate through the non-zeros in row 0, you start in position 0 in pointer, you see that it starts at 0, you go here, and you read up to 2. So the non-zeros in row 0 are bounded between position 0 and position 2 in the index. And more generally, if you want to read row i's non-zeros, you look at the start of some row I, and the end of that is pointer I plus 1, not inclusive. How do you bound it? Like, how do you know that the end is here? Yeah, good. So when you build this thing, like think about actually building this. So we would iterate through this linked list, and suppose that we knew the total number of indices, or suppose that we know the total number of non-zeros up front, and suppose that we know the total number of rows, if that's like given as the first entry in the file. And so pointer array, the length of this is equal to how many rows you have. And the length of this is equal to how many non-zeros you have. And then so the way you build pointer, the way that you build any of them is that you go through every non-zero in that row, you write its column ID here, and then since you know how many there were, then you can just write, you know where you started writing them, and you know where you ended writing them, which is just how many there were plus 1. Or just how many there were, like the previous one plus how many there were. And that's how the distances go. Like the definition of pointer is in every entry I, that is the start of row i's non-zeros. And so row I minus 1's non-zeros must have ended before that. I see. So are you saying that if there are many rows that don't have, so say there are many rows that don't have any non-zeros, you still have to store one position here? Yes, so you would waste that space because here, like for example, 2 or 1 has no non-zeros, so we just repeated this position. You can again, so there's, if it's called like hypersparse, which is that so many rows have nothing in them, you can again compress this thing. So that compress. So the main difference between dense and sparse representations is that in sparse representations, like here, you explicitly write the coordinate, or like in coordinate format, you explicitly write down the location of the non-zero, whereas in dense, like, you never explicitly write down the location, but it's implicit in the indexing. So this here is in some sense a dense representation, because you never actually write the ID of the row, it's implicit in the indexing. So theoretically, you could make this explicit. Like you could have tuples where you write like row and start position. So that's called doubly compressed. Any questions? Okay, so the reason that I wrote this up, well, there's many sparse representations. But one thing that you can try to do in your programming assignment is convert between COO and CSR and try to run the algorithms in CSR because it's probably faster. Okay. And then there's just this difference, like if you have an underactive graph versus a directed graph. An underdirected graph is a symmetric matrix because underactive means that every edge goes U to B and V to U. So that corresponds to the pair UV and BU in the matrix. So in CSR, you have several arrays. Suppose we're going to use N and Z to represent the number of non-zeros. Non-zeros, again, are just the elements that are actually there. You have an array of values of size N and Z, an array of column IDs of size N and Z, because every N and Z has some row ID, column ID, and value. But the row ID is implicit in the start pointers. And so that's why we only need to store column ID and value equal to length N and Z. And finally, there's the pointer array PTR, which has size equal to the number of rows. So there's one entry per row, which tells you where in the column ID array and where in the values array that row's non-zero start. So the total size of this thing is proportional if N and Z is, you probably have on the order of at least one non-zero per column, like on average. So if N and Z is greater than N, the total size is bounded by N and Z. Because usually non-zeros, the number of non-zeros is much less than N squared. This whole thing is much smaller than the desk representation in most cases. So this is all good. It's correct in that it does store all the entries in the matrix, but you can imagine that the problem is when you want to run algorithms on this thing. So previously we had done dense matrix algorithms, and that was easier to think about in some sense because you have, you have the 2D matrix, you have the vector, and you just cut up the matrix from the vector, and everything is there. It's like it's a full block, or it's just a vector, and you can just directly iterate through the full block, or iterate through the vector. But running algorithms on this thing is slightly more complicated, and that the way that the algorithms work depends on the representation, because every representation iterates through the non-zeros differently. CSR is probably the most common one, and we're going to just be using it throughout. First, just to illustrate the algorithms. Other common ones, compressed parse column is just, rather than storing in row major format, you store in column major. So instead of column IDs, you have row IDs. There's diagonal. So if you have this special diagonal matrix, you can store the main diagonal as a 1D array, or diagonal bands as a 2D array, and then you will have even less space because you don't need to store the column IDs. Because if you just know that you have the main diagonal, the pairs that you have are all like I. It's like row ID and column ID are equal, so you don't need to store them. You just need to store the values. And there's symmetric, which is if you know it's equal across the diagonal, you can just store the lower half, lower triangle. Then there's blocked, which is somewhat specialized. So blocked is, I'll talk about it more later or next time, but blocked is, if you have this special block structure, you can actually build representations to capture that. And that gives you some performance benefit because things are closer together. Yeah, so this is not a comprehensive list of formats. There are many, many sparse matrix formats, but if you know compressed sparse row, that already captures a lot of it. So for practical purposes, in your programming assignment, if you have a list of coordinates, you would need to know how to convert it into CSR. And then next we will go through some examples of how you run algorithms on the CSR. Any questions on that part? So first, let's just do the serial case where you have one processor. It is easier to see how the access goes. Just ignoring parallelism for 1 second. So for sparse matrix vector, so previously we've done matrix vector. And if you remember what's happening in matrix vector is that you have A, which is your matrix, you have X, which is your vector, and you have Y, which is your output vector. And for every row of A, you do the dot product between the row of A and the vector X. And the output of the dot product is one scalar, and it goes into the corresponding entry of Y. And so when we had dense matrices, the dot product was just like, you iterate through A and X at the same time. You do the multiplication of each entry, and you sum them up until the end, and then that's your output. But now we can't do that so easily because we have CSR, for example. So suppose we have matrix A in CSR, and the vectors are dense, X and Y. And we only want to, so when you compute the dot product of any row of A and the vector X, the only things that are going to go into the dot product are the entries where A actually has something in that row. And so ideally, we would like to only iterate through these real entries of A. And this is, you do that, so it's just 3 lines. For every row I, so this line, for k equals pointer of I to pointer I this one, this is what we were talking about earlier, which is how do you get the range of column IDs for row I. So k is now just going, k is going through the indices in these arrays, int and val, corresponding to row I. And so now we output into the upper vector y of I, which is the row, plus val of k times x of int of k. So val of k is pretty straightforward because k is just the index into this thing. But this part is maybe slightly more complicated. Why is this x of index of k? Because index of k is the column ID. Like you have to read it from the index array, and then use the column ID to index into the vector x. So basically what's happening, like, just look at this top row. Suppose that, let's read this one. This one corresponds to this, which is some column ID. This will give you the column ID corresponding to this entry. And then now you have to figure out which entry of X corresponds to that. So that's why you can't just directly do val of k times x of k. Because x of k is some position in this array, which has nothing to do with the position either in this row or here. So then you just repeat these two lines for every row I, and for every row I, the two n bounds. The start bound is in pointer I, the end bound is in pointer I plus 1. So from an optimization perspective, we make one single pass through the matrix A. So there's no possibility to improve the cache locality really, because we're never going back to any entry. Once we have passed the entry in A, we're done with it. However, and there's maximum reuse in Y, because once we have passed an entry in Y, like say we have accumulated all into Y0, now we move on to Y1, we're never going to go back to Y0. And so the only way that we can possibly do the optimization is to try to make the accesses into X more friendly. Because the way that it's currently written, the accesses to X are pretty random. Like it could be any, just depends on the column ID of the non-zero in A. So the main hard part is probably this indexing. You have to keep track of what is the column ID and how do you use the column ID to access the second operand. And the most basic operation that you pretty much use in all matrix algorithms is that you want to iterate through a row, or you want to iterate through a column. Like, for example, if you think about matrix, like you iterate through the rows of A and you iterate through the column of B. And the only time that you actually get anything in the output C is when the inner dimensions match up for A and B, like A, I, K times B, K, J. K needs to line up. So if any side of those are 0, like either AIK or BKJ, if either is 0, then it's not contributing anything into the output. And then we can skip that. So in terms of parallelization, the parallelization schemes are pretty much similar to what we have done before in dense matrix vector. So the first most straightforward way we can do this is we just stick a parallel 4 over the iteration over the rows. Because every entry of Y is separate. So that means every row, so what is contributing to every entry of Y is one row of A and some stuff in X. We are only reading X, so you can just read it for free in parallel. And if every processor is handling one entry of Y, then it just needs X and the row of A to do that. So that's why you can just put this here. And this thing is just the code that we had earlier. So for J, so every row, the row is I, J is the column ID, or the index into CSR is the column ID. Starts at pointer I, goes up to, but not including, pointer I plus 1. And then you use J to index into the values array, and temp is index of J. So here, temp is column ID. And the pair, the coordinate pair, So that just parallelizes over the rows. You can also do parallelization over the columns, so you can parallelize within the column as well. And one way you can do that is through prefix sum or scan. So suppose that we have X, which is this vector, and this is our A matrix in CSR form. The different colors are the different rows of A. So row 0 has two non-zeros because we know it goes from 0 to 2. So we have, so the non-zeros are 0, 1, and 0, 2. And the non-zeros in row 1 are 1, 0, 1, 3, 1, 4. That's how you read the CSR, and the values are just these given in the file. And the way you do, so every row or every entry in Y is a dot product between one row of A and the vector X. And you can do that through doing a prefix sum. So if you compute the product, so you can compute the products up front in parallel, which is just the product of the non-zero in A with the relevant entry in X. And if you do those in parallel, then you just need to accumulate them. And you can accumulate, so with product, you can just do this element-wise multiplication, and then to do the accumulation, you can do this segmented scan on the rows. And the last entry will be the result of the dot product. So that can be used if any one of the rows, so there are many issues with sparse problems. One main issue is load balancing. So in dense problems, there's never any problem because every row has the same length. And so you just cut them up by row and everything is equal. But now in sparse problems, if you cut them up, even if you cut the rows equally, like you have n rows, you cut them n over p, some work pieces will be larger than others because some rows will be longer than others. They have more non-zeros than others. So the work depends on how many non-zeros there are in the row. So there are some techniques to get around this, but they get more complicated, and like the easiest way is just if you cut along the rows. But then trying to cut the work evenly is like now you have to figure out how much work is in every row. Should I cut that? So it's a bit harder. This is just what I was saying. So you pre-compute the product to this array, and then you perform a segmented scan, and the last one in every row is what is going into 1. And yeah, so sparse matrix vector, every sparse problem depends, the implementation depends on the representation, but we're just doing sparse matrix vector because it's one of the original ones with the source somewhere. So if you have a diagonal format, you can do something even more special. So diagonal is like this, so you have like orange, blue, and red. You need to store the values, just the whole diagonal, but you can do something very optimized in storing the column IDs, because along the main diagonal, the column ID and the row ID are the same. If you go one up, like this red one, the column ID is row ID plus 1. And similarly with the orange one, the column ID is row ID minus 1. And so going on like this, then you don't actually ever need to store all the column IDs. You can just store the offset if you have such perfect diagonals like this. And then it becomes, then the algorithm only has to compute for every diagonal. You're trying to compute sparse matrix vector. You can parallelize over the rows, just similarly as we did in the previous case. But now, rather than previously, we were reading the column ID from the CSR. Now we can just do column is which is row ID plus column offset of k, which is which diagonal we're doing. That will give us, yeah, with some check that this is a valid number, then you can just directly compute the dot product like this. The value is like this, k is the row, column is which column ID you're in, times x of that column. So we do the dot product. The main point of this is that the high level is the same, which is that you want to go through the non-zeros, but depending on which exact type of format you have, it looks a little bit different about how you do that. Diagonal is also popular if you do have this nice diagonal format. Even if you have some empty spaces, you can still, if this diagonal is mostly full, you can still just write the zeros out here. And it's popular for GPUs and vector architectures because you can just parallelize it easily. There's not really any random access in X. You're just accessing X left to right. Questions? Are there any questions on, like, I guess two things you would need to know is one, how to convert from COO into CSR. Another one is how you iterate through the CSR, like through the pointer ID and the column ID. Okay for everybody? So, a few minutes left. We can talk about distributed a little bit, but parallelization is very similar to what we talked about when we were doing dense matrix algorithms. So, if you remember how we do it in a dense case, one way that is pretty straightforward is you have the matrix A, you cut it, so you have P processors, you cut the rows, if you have n rows and P processors, you cut the rows n over P, and every processor gets n over P rows of A. And then every processor needs all of X to do the dot product, and if it has those, then it can compute some n over P entries of Y. So this was the pseudocode that we had last time. If X was split up, you all gather X, and for all the local rows you have of I, you compute Y of I locally. And we can do this sort of partitioning, or we can do this 1D distribution for sparse matrix as well. The only difference is that A is now in CSR rather than in dense matrix form. Another one that we did last time was if you cut it by columns rather than by rows. And so the columns, if there's n columns, then you cut n over P columns per processor, and every processor has some part of X, and it can compute some partial of Y. And then in the end, you need to do this horizontal reduction across the processors to compute the total in Y. Is this familiar? I can't remember those goes. Yeah. I'm not going to do, I think we're just going to go through this again, like this is not new for the sparse case, but it just is different because cutting A is harder now. Previously, you could just cut it by index. Now you need to figure out, like, where to the row n, right? And then 2D blocked is just you cut it both rows and columns, and so you need only part of X, and you still need to do this horizontal reduction. So for in the sparse case, it's the same. We copy X So X is all gathered on every processor, and we can just cut the sparse representation. One slight complication. So if you think about, say you have a CSR, and you want to put the first n over p rows on processor 0, you want to put the second n over p rows on processor 1, and so on like that. You can't just directly ship off like the parts of the CSR, because starting at processor 1, the index is not 0 of the starting point. So you somehow need to offset the starting IDs and pointer. So, but you can do that either locally once you ship it, or on processor 0, you can modify the pointer ID, or you can modify the pointer array. If you have A in coordinate format, and if the coordinate format is sorted, it's easier, because just getting the first n over p rows means that you, well, the first one is easy because you just start at the beginning, and then you do like a binary search in the whole list for where does the n over p plus 1 row start, because that's just the next row after this partition, and then right before that is the non-zeros that you need to send to p0. One tricky thing also with X in sparse matrix vector is, so you can altogether X, and it would be correct because then you would have the whole vector. Theoretically, maybe you could do a little bit better, because maybe you don't need all of X for every one of these processors. Like for example, if you know that this thing is just one diagonal, P0 would only need like this part of X. P1 would only need like the second part of X, and so on. So if you know something about the structure, maybe you can exchange fewer elements in X. Yeah. And the last one, well, I don't know if this is the last one, but the next one is column partitioning. The partitioning is the same as in the 1D case. Another special thing that could possibly happen is if some of the, so you do like the horizontal reduction in this case. If some of the entries are empty, maybe you can skip them. Or like if some of the partials are empty, you can possibly skip them in the sum. But that also requires like knowing which ones may be empty. And then the last one is 2D partitioning. So I think we already give this in the handout for the programming assignment. Split up according to coordinate format in COO, which is a list of tuples. And yeah, so you can split this into 2D, and this is just, each one of these is a group of tuples corresponding to those non-zeros in A. And this is just, there's this benchmark in this parallel suite of benchmarks called NAS, and they implement this 2D partitioning scheme. So for sparse matrix vector, it doesn't make that sense if you get, it doesn't make that much sense if you get this in COO to convert it, to spend the time to convert it into CSR, if the COs is already sorted, because you only have to make one pass through anyway. But for other algorithms, it may be worth it to do the conversion, to spend some time doing the conversion, because if you go through it repeatedly. Yeah. So this is good because it, as we talked about when we were doing test matrix, it allows you to use more processors. But for any of them, if you just cut it directly by rows or columns, there may be some issue with load balance, because maybe all the non-zeros aren't here. And then so it's not so good, because then the whole thing is serialized in there. And I think I'm probably out of time, so we can continue next time. Yes, 1 second, sorry.